So again,
Yeah, I got it.
so the next type of orbitals are the p orbitals. If s orbitals are lowest in energy, the p is a little bit higher in energy. The p orbitals can hold, I wonder how many?
2.
1,
4.
2,
8.
3, 4,
But I thought
5,
all orbitals
6.
can only hold 6.
The p orbitals, there are 3 of them, so they can hold 6 electrons.
Oh.
There are 3 p orbitals. Each orbital can hold 2, so the p orbitals can hold a grand total of 6 electrons. The entire collection of p's can hold 6. So p's are a little bit higher in energy than the s. A little bit higher in energy than the s. And there are 3 of them, each one oriented on the 3D axis, one oriented on the x, one oriented on the y, and one oriented on the z. So there's 3 of them, xp, yp, and zp. Now, let's look at the green dot again. Level 1 is very low in energy. Level 1 can only hold an s. Hence, hydrogen and helium, 2 total atoms. Level 2 can hold an s and a p. There's your s, there's your p. In fact, if you were to assign an address to hydrogen, you would say, I'm in period 1, s shape, 1 electron over. Helium is also in period 1, also s shape, but it's 2 over. In fact, sometimes you see helium drawn over here. Because hydrogen, helium, this is what we're going to call the s block. Right here, we're going to call this column the s block. So frequently you see hydrogen and helium placed right next to each other. This is the p block. How wide is the p block?
6.
It's 6 atoms. If you were to look at, guys, if you were to look at lithium's electron configuration, what period is lithium in? 2. What shape? S. How far over? 1. Lithium's last electron is 2s1. Beryllium is 2s2. Look at boron.
2p.
Boron is in 2p. How far over? 1. Boron is 2p1. Carbon is 2p2. Nitrogen is 2p3. Oxygen is 2p4. And fluorine, 2p5. And then poor neon, right there with rip in it, is 2p6. Level 2, p block, 6 over. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So, with that understanding, does that make sense to you? Can you see that? You see the pattern?
What about just point?
If you see the pattern, then, guys, if you see the pattern, then what's sodium? 3s1. And magnesium? 3s2. And aluminum? 3p1. And silicon? 3p2. And phosphorus? And sulfur? And chlorine? And argon?
3p6.
3p6.
Wait,
Yes,
is there anything after p?
absolutely. Yeah.
Q.
There's this right here. And again, I don't know why it's the letters they are that they are. But so again, summary, the p orbitals are higher energy than the s.
Oh, I
We
love
put
these
6 of them,
dumbbells.
so we write it like this. Now, I do not know why there is the letter is written and then with an exponent, but it's not read as p to the 6th power or s to the squared. It's read s2 p6.
Wow.
I think that's just so you can squish all the electron configuration together. Okay. Give me a thumbs up if you're ready to talk about the next one. Does anybody know what the next one is?
Q.
No. D. Excellent. Yeah, I remember from your crossword. The d orbitals are next. The d orbitals are next. There are 5 d orbitals, and don't worry, I'm not going to ask you to draw the orbitals. For half credit for your test, draw the d orbitals. I'm not going to ask you for that.
What the heck is the last one?
It looks like a binky.
It does look like a binky.
Here's a binky.
Yeah, it's the binky orbital. That has to do with what are called wave equations, which are deal with the probability of electrons and where you can find them in space. And you can learn about that your 2nd or 3rd year in college. I'm not going to go into it here. Even AP chemistry doesn't go into it. So we're
Wow.
just that is the way the shape is. It has to do with a mathematical probability of where the electrons are going to be. If you want to learn that on your own, you can go to YouTube and just type in Schrodinger's wave equation, and it'll spit out why the orbital.
Do we have to learn how to write that?
Nope.
To spell it?
Nope.
Okay.
Yeah, it's the same Schrodinger with the cat thing. So Schrodinger is all about probabilities of electrons. He wasn't about cats, he was about electrons, but he used the cat thing to use an analogy. But anyway, so there are 5 d orbitals. Each orbital can hold how many electrons? 2. And 5 times 2 is usually 10. So it is no coincidence that the next block on the periodic table is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms across. Yeah.
Where did the 5 come from?
There are 5 types of d orbitals. Yeah. So an electron can choose to be in any one of these 5 types of orbitals, and that's how it works. So the d block, we're going to call this the d block from scandium over to zinc, is 10 atoms across. Scandium, it turns out, is 3d1. But Mr. Byers, it's in period 4.
It's supposed to be in 3.
It's supposed to be up here. Here's the problem. Level 3 is simply too low in energy to hold the d orbitals. The d orbitals are too high in energy, so they cannot fit into level 3. So they have to get pushed down here. Okay, we'll talk about this in a little bit. We'll talk about why it's pushed down in a little bit. But for now, just understand that the d orbitals are d10. This is 3d1. Titanium is 3d2. Vanadium is 3d3. Zinc is 3d10.
Oh, wow.
Make sense? Okay. The next type of orbitals. Okay, question.
Would yttrium be 4D1 then?
Yttrium would be 41. Yeah, yttrium would be 41. Other questions? All right. So the next type of orbitals are a little goofy. These are the rare earths, and the rare earths are F orbitals. There are 7 of them. So the F block is 14 atoms across. And these you will have to memorize how to draw.
Really?
I'm just kidding. No, absolutely not.
Gosh.
No,
I can
you-
do it. No, I'm playing. That one looks like a nuke upside down and right side up.
Yeah. So 4F14. There you go. So again, don't have to worry about drawing them. So electrons in your rare earths, nobelium, californium, uranium, protactinium, those are all chilling out in the the F block. Okay, how are we doing so far?
Good.
Okay, this next part's really fun.
Those are by 4 every time.
Yeah. Okay, are you ready? Give me a thumbs up if you're ready to move on. No. Okay, take 1 more minute. Scribble what you want to scribble. The bulk of it is down here. S2, P6, D10, F14. And if you're in the front row and you can see the electron configurations right here, there's the electron configuration. That's the entire electron configuration from hydrogen to oganesson. So all the elements that we currently know to exist or can be made. All right. So using this information, we can assign blocks to the periodic table. We can call this the S block. We can call this the D block. We can call this the P block. And we can call this stripe, which should end up right here, the F block. And again, for some reasons I do not know, some periodic tables will put lanthanum and actinium right here, and then have lutetium and lawrencium down here. Some will put cerium and thorium here, and some will put lutetium and lawrencium. It's just see, we built it with like our periodic table from Web Balance. We put lutetium and lawrencium right there, but there is no standard way to do it, because when you get atoms down here, kind of the rules get a little blurry. So people are like, I'm going to do it this way. So there's no standard way. Yeah.
What block are strontium and all the other ones?
Like 110 or 115.
Well, if they're below zinc, they're in the D block. If they're below boron, they're in the P block. So yeah, if they're down here, they're in the D block, and if they're down here, they're in the P block. Those crazy ones that only exist for a millisecond. All right. Now, electrons. Electrons have two primary states. And there's this thing called the Pauli exclusion principle that states electrons cannot be identical. No two electrons can exist in the exact same state. So if two electrons are sharing an orbital, one will be spin left, one will be spin right. One will be spin male, one will be spin female. No, that doesn't work. One will be spin spin X, and one will be spin Y. One will be spin dawn, and one will spin. Or instead, we're going to say they're spin up and spin down.
Oh God.
So one will be spin up, and one will be spin down. One will be spin black, one will be spin white. No, that doesn't work. One will be spin ugly, one will be spin pretty. So we just said, hey, let's make them up and down. Spin up, spin down. Are they actually spinning? No, they're not things. They're packets of energy. So they're not actually spinning. We just have to have a way to say one is this and the other is that. Spin this, spin that. So by convention, electrons are spin up or spin down. Any electron that is by itself is spin up. And any electron that must pair will be spin down. And Hund's rule says this. If you are filling electrons in orbitals, and there's more than one place for electrons to go, like in a p orbital, then those electrons are going to fill spin up first. In other words, if an electron has a choice, it's going to look at the orbitals and say, I'm going to be spin up there. Now, another electron comes in and has a choice, it's going to be, I'm going to spin up right next to you. It's kind of like if you threw a movie night. So Austin's like, I got Incredibles 2, come over and watch my movie. And in Austin's house, there are 3 love seats. Each love seat can take 2 people. Okay? So Anthony and Austin and Rafe, they go to a movie, they're having a movie night, and Anthony sits down in his love seat. And then, Austin sits down in his left seat, and then Rafe comes in and sits right down next to Anthony, and Anthony's like, guy, there's a whole love seat right there for you. And Rafe's like, oh, okay. And Rafe sits down in his love seat. They spread out. Okay, make sense?
Rafe, why do you gotta make stuff weird?
Okay, and then Gavin and Michael and Thane come in, and they're like, oh, cool, there's 3 seats. So they're going to be like, so Thane sits right on Anthony's lap. No, Anthony's not going to want Thane to sit on his lap. Anthony says, no, you sit right there. And Thane's like, okay, I'll sit right here. So if there are 3 electrons and there are 3 available orbitals, those electrons will each occupy their own orbital first. And only when you have to share an orbital will you spin pair. Now, Pauli's exclusion principle is what I said. You basically just can't have 2 ups in the same place. Okay? If you do that, you violate Pauli's exclusion principle, and now you have 2 electrons that are identical, and no 2 electrons can be identical in the entire universe, as far as we know.
Unless they're twins.
Well, this is the realm of quantum entanglement, where like maybe we can make them identical.
That's what I was gonna say.
Yeah. So right now it's all science fiction, but the idea is maybe we can force them to be identical, even if they're, so that's the ideal of quantum, but it's all science fiction right now. Yeah.
So what's so great if they're identical? Like, why would we want to do that?
Since the quantum realm exists outside of space and time, you could basically put 1 electron on Earth and 1 electron on Mars, and when you turn that electron, you turn the electron on Mars instantly, instead of over 18 minutes, or 8 minutes, or whatever the time is that it would take. So since ups and downs, lefts and rights, yes and no's are the function of a computer, you could technically have instantaneous communication over vast distances, instead of having to wait for information to travel. So, yeah. Kelsey will tell you all about it. She's really into that. Okay, so if you had 3 orbitals, now right now, these represent 3 orbitals. Sometimes orbitals are represented with boxes, sometimes they're represented with lines. So we're going to represent them with lines right now. If you had 6 electrons to fill, watch carefully. If you can't see this, you want to stand up. They would show this way. Okay? They would fill up, 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 and then down, down, down. Okay? So first, Anthony, Austin, and Rafe sit down, and then Thane, Michael, and Gavin sit down. Okay. So electrons will always fill all available orbitals up first, and only if they must spin pair, or if they must share an orbital, will they spin pair.
Sorry, I don't know that.
All through period 1, she was repeating me. She repeated me twice for doing period 1.
Alexa, repeat.
I was like, Alexa, repeat this.
Sorry, I don't know that.
I don't know, no idea what I did, but like, it would do to repeat the last 30 seconds I said. Like, for emphasis. Thanks, Alexa.
Thanks.
Okay.
Now,
So, electron configurations are the 1s, 2s, 3s, whatever. So the output principle says, first of all, electrons want to exist in the lowest energy orbital first. Much like you, me, the dog, and the planet, and everything else in our universe, we want to exist in a low energy state. It's the second and third law of thermodynamics. All things want to exist in a low energy state. So, here's the crazy thing. If you look at levels and shells, S shell or S orbitals are lower in energy than P, which are lower energy than D, which are lower in energy than F. S are the lowest energy orbitals. But here's the crazy thing. Shells nearer to the nucleus are lower in energy than shells further from the nucleus. And it is the product of the shell and its orbital that determines how energetic that electron is. The most energetic electron would, in theory, be in the 7f orbital. In reality, we don't have a 7f, we have a 7p. So in our galaxy, the most energetic electron we know about would be in the 7p orbital. The least energetic orbital would be a 1s, that in hydrogen. So then there's kind of an interesting query. Which is lower in energy? An electron in the 3d or an electron in the 4s?
Wouldn't it be 4S?
Would it be 3d or 4s?
4S.
3d. It turns out the lower electron is the 4s. The 4s electron is lower in energy than the 3d because the d is so high in energy. And that is why the 3d electrons are placed after the 4s electrons. Potassium is 4s1. Banana. Potassium is 4s1, calcium is 4s2. And then scandium is 3d1. 4s2, 3d1. 5s2, 4d1. 6s2, then the F, 5d1. Right? So the 4s fills before the 3d because the combination of 4 and s is lower in energy than the combination of 3 and d. Does that make sense?
Yep.
Okay. Give me a thumbs up if this craziness actually makes sense to you. Okay. Everybody but a few people in the back. They're scribbling madly. I wonder if you have, okay, cool. Okay, so this is kind of neat. This is a diagram that pops up every now and then on the internet and in textbooks. Level 1 can hold the S. Level 2 can hold an S and a P. Level 3 can hold an S, a P, and a D. Level 4 can hold an S, a P, a D, and an F. Let's fill these up. The first electron in 1s would be up. And you show with a little half arrow. That's just the way it's done. The second electron would be down. 2s. What's the first electron going to look like? Up, and then
Down.
down. 2p,
Up, down.
up, up, up. Remember Hund's rule.
Yeah.
The p electrons, there are 6 of them, 3 orbitals, so we're going to fill up, up, up first, and then down, down, down. 3s, up, down. 3p,
Down, down, down.
and then the 4s fill. It fills up, down, and then the 3d fills. How many orbitals are in the d? 10 electrons, and how many orbitals? 5. Up, 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 and then down, 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 down. Then the 4p does its thing, and off we go. Okay? By the way, it doesn't show the 5s, but the 5s would actually be right here. The 5s would be after the 4p, before the 3d, or before the 4d. Yeah.
Do the numbers before the letters really?
They tell you the level, the principal quantum level. So yeah, they're very important. So this number here, these are the primary principal quantum numbers, the level of the electron. So yeah, it's important. Okay, so off we go. I drew this just because it's fun. So if you were looking at all the electrons that we're filling, you would first fill the 1s2, then the 2s2, so 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3d10, then 4p6, then 5s2, then 4d10, then 5p6, then 6s2, then 4f14, then 5d10, then 6p6, then 7s2, then 5f14, 6s, and you get the idea. So, if I was to ask you, what is the electron configuration of oganescium, you would reply 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. That whole thing is the address of oganescium. We're going to learn next time, or next time, that there's a much easier way. Thank you. Yeah.
Why does the debug start at 3?
Okay,
Oh, yeah.
guys, pause.
Great question.
Pause. The question was, why does the D block start as 3? And the answer is, level 1 and level 2 are simply not high in energy enough to hold a d orbital. The lowest energy that can hold a d orbital is level 3. That's why D starts at 3. Similarly, the f orbital is too high in energy to be anywhere but 4, 5, and 6, and 7.
Oh.
So the first f is 4f. Question?
So is there like some pattern you can use to memorize that or something?
Absolutely, right there. So you can start 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. I wouldn't memorize it at all. I would just use the periodic table as a tool. So, that's a good idea.